We can go ahead and turn off the music. It's 3:07, and I thought I'd tell you a little bit about my trip to England. And keep sending the jokes, by the way. I know we haven't read many, but I forgot to send them to Nicholas, but I'll start reading them on Friday. Anyway, I went to England to accept, as part of two large teams, the 2007 Gruber Cosmology Prize for the discovery that the universe is accelerating in its expansion. And the ceremony took place at Cambridge University, but specifically at Trinity College. And that's the place where Isaac Newton was both a student in the early 1660s and then a professor starting around 1667 or so. So there's sort of Newton paint portraits and things like that all over the place. This is part of Trinity College. I think this is the window to Newton's room, but I need to email one of my colleagues who knows these things. Maybe it's that one. But anyway, I'll find out where Newton used to sit and spend a lot of his time. As I said, portraits are all over the place of him. So there I'm looking at Newton. Can we turn down the lights that are right on the screen, please? And you can keep the backlights on. Thanks, Alberto and Nick. Yeah, that's very good. Thanks. So actually, if we go back to, don't know how well that turned out. Yeah. There's Newton looking at me, and I'm looking at Newton. So anyway, there's Newton's chair. That's a chair that he used, okay? So it's preserved, and they wouldn't let us sit in it. You can see there's that little barrier on top of it. I'm sure tens of thousands of people would like to sit in Newton's chair, but they don't let you do that. In fact, it's not even a museum. This was in a special room where one of the celebrations took place, next to a portrait of his. And here in the garden of Trinity College, there's an apple tree. And this is, of course, not the apple tree, because it would be an awfully old tree, kind of like the bristlecone pines or the sequoias. You know, apple trees don't last that long. However, there's a little sign there, and it says that this tree was descended from the tree at Woolsthorpe Manor. Yes, presented to Sir Michael Atiyah, Master of Trinity, on his retirement in 1995 as president of the Royal Society by his fellow officers. Anyway, so this is a baby of or a grandchild of the proverbial Newtonian apple tree. There's a member of the team with which I'm primarily associated, the High Redshift. That's what the Z stands for. I'll tell you more later about what Redshift means. Supernova Search Team. And this guy looks quite precocious, especially since we published these results 9 years ago. But it turns out he's the son of one of our members who passed away since then. So we thought it's appropriate that he be in the photograph. His name is Robert Schammer, in honor of his father, who was Robert Schammer as well. And all but two of our team members could make it to this celebration, so that was fun. And here I am with Peter and Patricia Gruber, who are the people who sponsor this award. And this is one of the few photos you'll ever see of me wearing a coat and tie. I typically do not wear coat and tie, okay? So anyway, here are Brian Schmidt with some weird reflection off of my camera and Saul Perlmutter. Actually, looks like I need to clean my lens because there are reflections all over the place at the fancy award dinner later that evening. And this guy was actually the guy who wrote the press release about the work that we had done. And here we are at a pub afterwards. There was a lot of going to pubs in England, you know. That's what they do. And if you can afford the prices, it's a lot of fun. But let me tell you, the prices right now are horrendous, especially in London. Late at night, we needed something to eat, and the only place nearby was a Burger King. And a Whopper without fries and without a drink, just the plain Whopper with cheese, was over $6.50. Like, yeah. The prices are the same or a little bit more numerically than U.S. prices, but there's $2.1 per pound right now. So, you know, beer or whatever at the pub cost quite a bit. Anyway, my wife was there, and she had fun as well at the pub. Going back, this is, yeah. This is Adam Reese, the guy who was a postdoc in my group when he, on our team, was the first to realize what the data were trying to tell us. He had been charged with working on the data, and I'll tell you more of the story later on. And this is a subsequent postdoc, Saurabh Jha. This is Adam Reese and Saurabh Jha. I'll tell you some stories about him in a minute. Anyway, and there's my wife, Noelle. And then we went punting on the River Cam. Okay, so this is sort of a fun activity to do in Cambridge, where you stand around, where you sit in these boats, and one person stands at the end and tries to keep his or her balance and pushes off the bottom with a long pole, and you kind of propel yourself along this river, which is more like a lake. It hardly flows. It's a very slow-flowing river. So I tried my hand, and it took a little while to get going, but I got used to it. And there's my former postdoc, Saurabh, and his wife, Frances. So, and some people would fall over, you know, because they lose their balance, but I didn't fall over. It was good fun. Here I am. See, I still haven't fallen over. And there are other punters, too, so they collide with each other once in a while, but fortunately at about a speed of 0.5 mile per hour. You know, you're going really slowly, if even that fast. And then after a while, Saurabh wanted to take a turn, so we switched, and we managed not to capsize the boat. And he did well, you know, for a while there, and there we are. There's my daughter, Capri. She's 1.5 years old, yeah. And but then at the very end, yeah, we were docking, and he was very carefully docking, and in a minute we would be all off the boat, but some other dudes came by, and they were going way too fast, considering they were about to land, and they crashed into us, and they knocked Saurabh overboard. And his iPhone got wet, you know, and he told me this morning that miraculously after 2 days it started to work, except for a few functions. But anyway, he took it all like a good sport and stuff. So here's other team members from our team kind of yucking it up about Saurabh. But safety notice, risk of falling. I just noticed that, you know. So, and then, oops, oh, sorry, I'm not sure why that's there. Am I going forward or backward? Oh, then we went to London, and I had to go to the Royal Albert Hall because, you know, now I know how many holes it takes to fill the Albert Hall. Some of you will get that reference. Some of you won't. If you don't, come on, the Beatles are the greatest ever, right? All right. Now they know how many holes it takes to fill the Albert Hall. You know, I'd really love to turn you on. Anyway, okay, so I didn't count all the holes. And then the last evening we went to a theater. We went to We Will Rock You, which is sort of the story of Queen and how they came to be and everything. And that was really fun. But the music was too loud, so you couldn't hear the words and stuff. But it was good. You know, you can't go to London or New York or whatever without going to the theater. Then I came back to my room, and it was 11 o'clock at night, 11:05, and I realized it's 3:05 Monday in Berkeley. So I went to webcast.berkeley.edu, and I watched Nicholas's lecture. See, look at that. There he is. Nicholas, where's Nicholas? Is Nicholas here? Well, I thought Nicholas did a great job on both lectures. Where's Nicholas? Oh, there he is. He's hiding. All right, Nicholas. In case you didn't hear last time, here we go. Right, so yeah, see, it doesn't say the time here, but it's 11:10 at night in London, and you didn't play the song I gave you to play, but that's okay. I told you could play whatever song you wanted to. What'd you play on Friday? Oh, okay, that's fine. Well, I don't know about this one. I'll have to listen to the words. Does it have anything to do with astronomy? That's okay if it doesn't. I don't care. Anyway, you did a great job. And I'm especially proud of the fact that Nicholas knows that I like to take photographs of various thingies, and he showed you a picture of a thermostat that I took in a hotel room. Well, I didn't know, I knew he would show it because I had it in the PowerPoint file, but I didn't know he would specifically point out that I like to take such photos, but I do. And so not to disappoint you, on the bus from Cambridge to England, in the bathroom, or actually in the little wash basin next to the bathroom, they had, you know, the red and the blue, and look at that. They assume you're so used to thinking that red is hot and blue is cold that they don't even label them. And I tried them, and indeed, red was hot and blue was cold. But remember, that's not the way it is for black bodies. It's the opposite. And it's not the way it is for light reflected by objects that are not, black bodies. But anyway, I just thought you'd like to see this. And by the way, you shouldn't drink this water. But anyway, that's what that sign means. So anyway, it was a good time. I'll tell you a few more little stories on Friday, and I'll get back to the jokes and stuff. Okay, let's start in. So a few things. Star party tomorrow night. Tonight would be a wash, I think, anyway. But maybe by tomorrow the marine layer will go away. Homework 2, due this Friday. Some of you still don't have course readers, but I'm told that NEDS finally agreed to dismantle some of the packages. So if you go to NEDS, you can get the reader as a standalone thing for, I don't know, 20 or 25 bucks, something like that. So you should all be able to get this, okay, if you go to NEDS. I think the ASC bookstore is sold out. And in the next 2 weeks, I'll have extended office hours to make up for the time that I missed this past week. How about, in addition to today's normal one after class, I'll have one before class on Friday and the usual one after class on Friday, but I'll extend it a little bit. But don't go turning in your homework after 5:15. This doesn't mean that you can turn your homework in at 5:30. It's still due at 5:15. But if you just want to gab about anything, I'm willing to stay until 5:30. And next week I'll have additional office hours as well, okay, to be announced. Okay, and then there's a quiz and discussion section next week, okay? And as Nicholas explained, it will never cover the material in the lecture immediately preceding your discussion section. But the penultimate one is fair game, and any of the ones before that are fair game as well. Okay, and then finally, Monday is the due date for this optional assignment. If you want to learn more, look at page 9 of the course reader. But if you really want to go to the Lick Observatory and see how research is done, write me an essay, compose a poem, a song, give me a collection of songs, whatever. Do something that convinces me that you really want to go and deserve to go, and will be funny and interesting to keep us up until the wee hours of the morning, okay? But you will not look through a telescope there, okay? I emphasize that because some people have won these trips and ended up being very disappointed when they ended up not looking through a telescope. But it will be that telescope which we'll be using, and it's got a 3-meter diameter mirror, and now all of you should be able to tell us why the size of the mirror is what's important, not so much the length of the tube. And indeed, to make telescopes cheap, we're trying to make the tubes more and more open with more and more shorter and shorter. Sorry, I'm still a little bit jet lagged with time, because the shorter and smaller the tube, the cheaper in general is the telescope. But we do want to maximize the size of the primary mirror. Okay, so just to review a little bit of what Nicholas said. He said that twinkling of stars is caused by different layers in the atmosphere moving around every which way, and they bend light ever so slightly. And because they're always moving, the light gets bent into slightly different directions at different moments of time. So sometimes the light will be bent toward you, sort of focused toward you, and sometimes away from you. So that's where the stars twinkle to brighter and fainter states. And the situation is much like what you would see if you were at the bottom of a swimming pool. I like to go to Hawaii. This is a photo I took in Hawaii. I kind of crash the hot tubs in the swimming pools. There's a hot tub whenever I go observing at the Keck Telescope in Hawaii. But anyway, this is very interesting, because if you were sitting at the bottom of a pool, you would see this. You would see the sun being alternately bright and dark as regions where the light rays by chance coalesced together reach your eyes, and then a moment later your eye will be sitting on one of these dark spots, not because you're moving around, but because this pattern is moving around, because the little waves on the swimming pool are moving around, and they cause this twinkling effect. So you would see a twinkling sun, a rather strongly twinkling sun, if you were at the bottom of the swimming pool. So our atmosphere does the same sort of a thing, but just not to such a great extent, because the density of our atmosphere is a lot less than the density of water. Okay. So, and this is all related to blurring, by the way, of a star's image. It doesn't look point-like anymore. And Nicholas told you that a star twinkles quite a lot. This is Sirius, near the horizon, twinkling quite as much, whereas a planet twinkles a lot less. And that's because a star, though it's big, is so darn far away that even through a telescope it looks like a point of light. Whereas planets through a telescope can readily be discerned from a point of light. They look like a disk, and some of you have already seen Jupiter through the telescope on the roof of Campbell Hall. So it's like you have a whole bunch of independently twinkling points of light. sort of 1,000 points of light, if you know what I mean, and they kind of average each other out and cause a more steady light, and that's why a planet twinkles less than a star does. Okay, well, this twinkling is related to, but not exactly the same thing as, blurring of the image. And so a short exposure of some stars shows that they don't appear like true points of light. Rather, they look kind of smeared because of this blurring effect in the atmosphere. And here's a nice example of this blurring effect, where if you observe a star many times per second, you can see that it's at each moment of time all smeared out, and the smeared out pattern moves around with time because the layers in the Earth's atmosphere are all constantly moving around and bending or refracting the light every which way, moment after moment. But there's a way of correcting for that using ground-based telescopes, and it's known as adaptive optics. And it's a fantastic thing because it allows you to get the clarity from the ground that you would normally achieve only from space. And in fact, with the Keck telescopes, which are a factor of 4 bigger in diameter than the Hubble Space Telescope, 10 meters versus 2.4, you can actually get better clarity from the ground using the Keck telescopes than you can using, say, the famous Hubble Space Telescope. That's not to say the Hubble Space Telescope wasn't useful. It was a magnificent instrument, has many uses, okay? But over small fields of view at some wavelengths, you can actually do better from the ground. And the point is that we correct for this blurring effect, creating a star image with the clarity that you would have achieved using that telescope had there not been any atmosphere at all, or very little of an atmosphere. I mean, you can see the star is still shimmering a little bit, but it's not shimmering much compared to this one. Somebody might say, "Oh, this sounds like black magic. How do you do this?" Well, it's not black magic. It's a well-tested and theoretically well-understood technique. Basically, you monitor the light of a bright star next to the object that you want to study. And if you look at that bright star many times per second, and you know that it's supposed to look point-like, and you see how distorted it looks, you can use the measured distortions of the bright star to apply a correction to a special little deformable mirror in the telescope system that will undo the distortions of the atmosphere, making that bright star look like a point, and any object within a short angular distance away from it, that is right next to it in the sky, will look clear as well, because the distortions affecting the light of the bright star are, to a good first approximation, the same as the distortions affecting an object right next to the star. Now, if you look way far away, your star is there and your object you're studying is over there, then you're looking through very different parts of the atmosphere, right? So then the distortions will not be the same. They will be independent. But if you look at an object right next to the star that you're studying, then the distortions will be highly correlated. In fact, they'll be nearly the same. So applying a correction based on the bright star will allow you to correct the image of the thing you were studying. And I think this is all written on that slide. So suppose you're studying this galaxy here, and it happens to have a bright star next to it. You can measure the light from that bright star many times per second and apply this correction factor. Here's how it's done, and don't worry about the details of this diagram. No way will we ask you to reproduce this or explain it in any detail on the tests or anything, but just get the general idea. Light, it says from the telescope, but it means from a star going, through the telescope, has these distorted wavefronts. That is, if you join together the crests of the waves, instead of being plain parallel straight lines like these dudes over there, they're distorted because they've gone through layers of different density in the atmosphere, okay? But from one to the next, they're pretty highly correlated. That is, one wavefront looks like the next one in time pretty closely. They change over time, but over a short amount of time, the consecutive ones are basically the same, and that's because the atmosphere doesn't change more quickly than, on sort of a few times per second. But if you measure every hundredth of a second, then successive hundredths of a second will be basically measuring the same atmospheric distortion. So what you have here is a mirror, okay, which is deformable. And it can completely negate these distorted wavefronts because the light bounces off of this mirror, goes through a thing called a beam splitter. So part of it goes through your detector, and part of it goes through this so-called wavefront sensor. Now again, I've just drawn lines that connect up the crests of a bunch of waves. So here's the crests of one wave, here's the crests of the next wave, here's the crest of the next wave, and you can see they're distorted. But this little wavefront sensor senses the shape of these distorted waves. And it does a bunch of computations. You need really fast computers to do that. And it analyzes the wavefronts and sends commands to a little tiny deformable mirror, which deforms the shape of the mirror in such a way that upon reflecting off of that mirror, the distortions in these wavefronts go away, and that they now look corrected and nice and plain parallel, and that gives you a nice sharp image, okay? This is a fantastic thing, all right? And here's a little animation that shows this process at work for the Gemini 8-meter telescope, which is on Mauna Kea volcano in Hawaii. So these are your taxpayer dollars at work, okay? But let me show you what's going on here. So you've got light coming in. Hope we can see that. Yeah, here. Light's coming in. Yeah, you can see it. Bouncing off the primary, bouncing off of the secondary, going through a hole in the primary mirror. And it enters an instrument compartment down here. And let's look at one of the regions of this instrument compartment. Let's cut one of these things open. This is the thing that has the deformable mirror and the wavefront sensor and so on. And the detector that detects the light. So light is coming in, okay? It hits this mirror, goes through a beam splitter. Part of the light goes to your detector and ends up being registered as an image on your computer. And you can see the image is all jiggling around and blurry like what I showed you in that previous animation. Now, however, let's see what happens when you turn on the adaptive optics unit. You've got all these plane parallel waves that are distorted. They should have been plane parallel, but they're all coming in. They get measured by this thing here, and an analysis system analyzes the wavefront sensors and sends corrections to this deformable mirror so that when, oops, did I stop it? There it goes. So that when the distorted wavefronts come in, they get fixed. They get corrected to be plane parallel, and there they all are scooting toward the detector. And when they hit the detector and get converted to an image on your computer, you can see how good it looks. I mean, it's fantastic. Now, despite really liking this animation, there was one great flaw in it, of a subtle nature, but not so subtle if you were listening carefully to what I said. Did anyone look carefully enough at this animation to see what was wrong with it? Anyone want to venture a guess? Way in the back there. Okay, the question is, why wouldn't the beam splitter immediately form plane parallel waves? That's because after hitting the beam splitter, the part of the waves that went through it needs to get analyzed by a rather complicated set of electronics and computers. And only then can you send a command or a series of commands to the deformable mirror to correct the next couple down the line. Okay, so that's not quite it. Remember, you're measuring some wavefronts to correct the next couple down the line. That sentence there contains the key to the problem with this animation. Yes, Brett. Yeah, Brett's saying that you're effectively saying these wavefronts don't look similar enough to one another. Remember I said that consecutive wavefronts have to look quite similar. Otherwise, if they look totally different, if you measure one wavefront and apply a correction to the deformable mirror, and then the next one down, or four wavefronts down, it looks totally different, the correction will be incorrect. So I think that's what you were saying effectively. You're always a couple of steps behind. Now, if the wavefronts, if like 9 or 10 of them in succession are pretty similar to one another, then though you're a couple of steps behind, it's okay. It doesn't matter. At least doesn't matter much. Of course, you'd like to be instantaneous. But if you looked carefully at this, and no astronomer besides myself that I've ever talked to has actually ever noticed this, but I'm a perfectionist, or I just notice details or something. I don't want to play it again. I don't know how to speed it up. But if you notice, the successive wave fronts in this animation were very different from one another. So the correction learned from wavefront number 1, when applied to wavefront number 4 after a time delay, wouldn't have worked. But in real life, they work because wavefront number 4, in fact, does look a lot like wavefront number 1. Nevertheless, having spent so much money making a snazzy animation, you'd think they would have done it right, right? Well, oh well. Oh well. It's pretty good other than that. You know, it's a pretty darn good animation. So anyway, that's the end result. Yeah, question back there. Your question is, the atmosphere doesn't shift things enough to make it a problem? Oh, yeah. So that's right. So in a swimming pool, the point that's being made is the water is so dense and changing so rapidly that the things on the bottom of a swimming pool are flickering on a time scale less than 1 second, much less than 1 second. Whereas with this, what happens is, I've forgotten exactly the coherence time, and it depends on which observatory you're at and blah, 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 but some fraction of a second, for some fraction of a second, the consecutive wavefronts look similar enough that this technique works. Yeah, so it's not like, if you measure number 1, then number 2, like, you know, number 1 looks like this. I'm a wavefront now, right? And number 2 looks like that, and they're all like doing this. They're all like, no, they're kind of like, they're shifting slowly, kind of like if you were to look at me with a stroboscope. You know, I'm slowly changing with time, and from 1 second to the next, I've changed a lot. But within 1 second, I haven't changed very much. Yeah, okay, cool. Yeah. Mm-hmm. Why is the corrected image so small? What's your name? Ina. And what's your name? Russell. Okay, Russell and Ina. Good. The corrected image looks so small because the Gemini 8-meter telescope, or Keck, or whatever this was done with, the previous animation was Gemini. I think this was Keck data. It might have been Lick data. But in any case, even the Lick 3-meter telescope, in principle, gives you a very clear image, much clearer than the typical image you get after the light has gone through the atmosphere. The point is that these mirrors are so big, and Nicholas said that the bigger the mirror, the greater the clarity, and there was even that little 3-panel image we have where first you're looking with the eye, and the 2 stars looked big. Then you look through binoculars, and the 2 stars looked smaller, but the same separation between them. And then through a telescope, the stars looked like little tiny points. So the clarity improves the bigger the mirror, or, lens of a telescope. And with a big mirror, you get a very nice, small, clear image intrinsically, except for the atmosphere. So yeah, that's the secondary purpose of telescopes. The primary purpose is to collect more light. For many years, the secondary purpose was to get greater clarity, because in fact, with bigger telescopes, you didn't really get greater clarity because the atmosphere would muck things up. I would say that now the tide is turning. Many astronomers build bigger telescopes, not so much for the purpose of getting more light, but for getting greater clarity using techniques like this. And then at radio wavelengths, I think Nicholas mentioned how with radio arrays, you can have a whole bunch of telescopes, and you can combine the light from all the dishes and get the effective clarity of a telescope as big as the outer extent of all those dishes. Like, how many of you have seen Contact, the movie Contact, where, you know, what's her name, Arrow Elliway or whatever, is using, what's her name? Jodie Foster, I know, but she's playing Ellie Arrowway or something like that. And she's sitting there listening to signals from ET. That's not the way that astronomers do it. They collect data with computers and detectors, and listening is not a very good way of collecting data and archiving it. But anyway, she was using this thing called the Very Large Array in New Mexico, which is humongous, but it has the clarity of a single dish that big, but not as much so-called light gathering power. On the other hand, it would be prohibitively expensive to build a single radio telescope covering, you know, whatever it is, 30 square miles on the desert of New Mexico. So we take what we can get. Okay, so here's some examples of adaptive optics in use, and I'll show you more throughout the course of the semester. Here's Io, one of Jupiter's moons. without adaptive optics, imaged with Keck, and with adaptive optics. Okay, and these blobs and stuff are volcanoes. Io is the most volcanically active body in the solar system. I'll tell you why later, but it's got like 100 volcanoes going off all at one time. We'll study it, like I say, later, but it kind of, to me, looks like a pizza. So I think I mentioned that in the first lecture. So if we ever have a chance to eat pizza together, maybe you can order an Io pizza. You know, we could suggest that to Laval's or Zachary's or something. Then you might ask, well, what if your object of interest doesn't have a star next to it? There aren't bright stars next to most objects of interest. So then you might say you're hosed. But with today's technology, we can create a star of our own, a fake star, by sending a laser beam up along the axis of the telescope and exciting a thin layer of sodium atoms that happen to exist about 90 or 100 kilometers above the Earth's surface. There's a layer of sodium atoms deposited there from by meteors, basically by little chunks of rock flying in from the solar system and disintegrating in the atmosphere. They have some sodium, and the sodium hangs around up there. And if you use a laser of the proper frequency, you can excite those sodium atoms and cause them to glow, creating a fake star right next to whatever object you want to study. And this is called laser guide star adaptive optics, where you create your own fake star. And this kind of looks like the death ray coming from, like we're zapping enemy spacecraft or something. Reagan would have liked this, Star Wars and all that, you know. So, but no, we're just trying to do science. Okay, this has, well, it does have military applications. In fact, the military developed these techniques long before astronomers did, but now they've become declassified and we can use them on our telescopes, which is wonderful. Okay, so that's if you want to create a guide star next to the star that you're studying, like, you know, whatever. Any questions on that? Yeah, over there. Yeah, adaptive optics, okay. Yeah, the question, and your name is Kevin. Kevin says there are only certain wavelengths that are transmitted by Earth's atmosphere. So can we use this at other wavelengths that are not, and is there any way to, you know, in a sense, remove the effect of the atmosphere using this technique? The answer is no, we can't use this technique at wavelengths that are not transmitted by the atmosphere. And though we would like to blow a hole in the atmosphere along that laser beam, unfortunately the laser beam doesn't do that. It doesn't create a little tiny tube through which the telescope could look. That would be really groovy. Maybe you could patent that. You can invent it first and then patent it. Like, you're not destroying the whole atmosphere, but you're just carving out a narrow little hole in the atmosphere through which astronomers can peek. Would you have to put some radiation protector? What's your name? Chris. Well, if you cut a hole through the atmosphere, you don't have to protect anyone unless you happen to be aiming it at someone who happens to be flying around up there, you know. So if you avoid planes, and we have to avoid them as it is. This is a very powerful laser, and pilots are afraid of getting blinded by this thing, at least temporarily. So we can't aim this thing at aircraft. If we do, they close us down. If we even aim it anywhere in the sky, when an aircraft is within even a few miles of the observatory, they'll shut us down. So we're very careful about shutting down the laser before any aircraft get close to the observatory. But no, we can't do this unless the light actually already makes it through the atmosphere. And by the way, also, this technique works better the longer the wavelengths are. And so it's been perfected at infrared wavelengths, but we can't yet use this technique at most visible wavelengths because it's harder to do at higher frequencies and shorter wavelengths. Yes? Yeah, the laser is visible like that. That's the question. Is it really visible? Yeah. This is not an enhanced picture. You can see the laser. The clearer the air, the less visible the laser is, because the laser is visible only by reflecting off of little dust particles and molecules in the air. So this is admittedly a time-lapsed photograph. You can tell because the stars look elongated here. At Keck, the air can be very clear and it can be a bit difficult to see the laser. But down at Lick Observatory, the air is usually not as clear and it's really easy to see the laser beam. You can even see it at Keck. Some nights more than others. It depends on how much dust is being blown around by the winds. It's a very windy place. I mean, it's like really windy usually. Okay, let me move on. Let's discuss a few atmospheric phenomena. It's 3:42. and 42 is one of the greatest numbers in the universe. So why is the sky blue, and why are sunsets basically yellowish, orange, or even red? It turns out that the molecules in the Earth's atmosphere scatter or reflect photons of light or waves of light. It bounces off of them, and so light that's coming your way bouncing off of a molecule might not actually reach your eye, so it goes somewhere else, okay? And it turns out that the blue wavelengths are scattered by molecules of air more readily than the red wavelengths are, okay? And that's fairly complicated physics. Let's not get into that. But just take it from me that blue light, short wavelength light, is more easily scattered by molecules of air in the atmosphere. So let's suppose you're sitting around here and it's noon, and let's suppose you look away from the sun. So you're looking in these directions here. The photons that are most likely to be scattered are the violet, blue, and green ones. Now, the sun, being relatively cool, doesn't emit all that much violet light, and blue scatters more readily than green, even though there's more green than there is blue. So when you take all that into account, the dominant color perceived by our retina and our brains from the sky away from the sun is blue. You might think it should be violet, but again, there's not as much violet light from the sun, and also our eyes aren't as sensitive at violet wavelengths. So it's some shade of blue. And the yellows, oranges, and reds tend not to be scattered, and they make it down, and they're viewed by someone over here, okay? So sunlight is white light. It's the definition of white light, okay? But the light scattering off of molecules in the air looks blue. It also scatters off of dust particles, and that too preferentially scatters blue light, but not as preferentially as scattering from molecules. Molecules really love to scatter blue light. But dust also scatters blue light, and more importantly, dust and smoke and smog and things like that absorb blue photons a lot more readily than they do red photons. So dust and junk, smoke in the atmosphere absorbs light, and it absorbs the blue light a lot more than the red. So let's consider what's happening as the sun gets closer and closer to the horizon. You can approximate our atmosphere as being a certain thickness and then a sharp cutoff. It isn't that way, but this is not a bad approximation. So here we are standing, and at noon, the light is going through the smallest amount of atmosphere possible, in a sense, okay? And so the light from the sun has been scattered out, but not much, so it basically looks like white light. As the sun gets closer and closer to the horizon, you see that the path that the light takes through the atmosphere gets longer. In fact, it's really quite long here. And all along this length, the violets, blues, and greens will, A, be preferentially scattered out of your line of sight, so they're not going to be the ones that reach you, and B, smoke and dust and smog is going to not only scatter light, but also absorb light, and again, preferentially the blue, okay? The blue photons are the ones that are preferentially scattered and absorbed. So as you're looking through a longer and longer path through the atmosphere, the cumulative effect of this preferential scattering and absorption of blue light leads to a progressively more yellow, then orange, then red image. And the smoggier the day is, or the more smoke there is from like all the wildfires in California and stuff, the redder the sun will be when it's setting, because there will be more and more particles absorbing the blues and greens and violets and letting the yellows and oranges and reds pass through. All right? So, in fact, here's a fantastic sequence of photographs taken by one of my favorite photographers, actually a mathematician in Finland, Pekka Parviainen. And he shows the sun at different altitudes over, I don't know, Helsinki or something, I'm not sure. And you can see it gets progressively more yellow, orange, and red. This is the same day, okay? He just took a sequence of photographs, and you can really see this effect. And all of you have seen the setting sun, and it looks yellow, orange, and red. And I've even gotten a few emails from perceptive students who have asked, based on Nicholas's lecture on Friday, is the red sun a physically cooler sun than than the white or yellow sun? And the answer is no. It only appears red because the light from it has been modified by our atmosphere. The sun's actual temperature is not changing. Nothing about the sun itself is changing when it's setting. It's just that your perception of the sun is changing because the light has gone through this filtering effect produced by our atmosphere. Yes? You said your name. I'm sorry. David, I didn't ask you last time you guys raised your hand. Okay. David. So David is asking, is the reason that the sky looks blue is because it's constantly absorbing and re-emitting the blue photons? Technically, you're correct. The scattering, the reflection process actually is a temporary absorption and re-emission. But it's not to be confused with the process I illustrated last Wednesday. You're not going from one level to the other in quite as clean a way. You can think of it more as just bouncing off. But the bouncing technically is an absorption and a re-emission, but for the purposes of this class, think of it as just bouncing. So it's not absorbing and re-emitting the way dust does. Dust absorbs blue light, gets hotter, and then re-emits it at infrared wavelengths, and that's not what's happening here. This is much more of a bouncing effect. Yes? So why are blue photons more preferentially absorbed? It's complicated. It has to do with the fact that the blue photons have a higher frequency than the red photons, and their oscillating electric field, remember last week, is able to cause the electrons and molecules to vibrate more strongly than the red light's electric fields. And so the vibrating electrons in the molecules absorb and then re-emit this light more readily than they do red photons. Okay, but it actually is quite complex. But it's a very, for those of you who are mathematically oriented, it's a very rapid function of frequency. It's proportional, and this is just an aside for those who are interested. The effect is extreme. It's proportional to frequency to the fourth power. So a photon that has twice the frequency of another photon has 16 times greater likelihood of being scattered by a molecule of air. This is known as Rayleigh scattering. Don't worry about it. Anyway, here's the rising sun as seen from Lick Observatory over the Sierra Range, and you can see it looks kind of yellow and stuff. So that's kind of nice. And here, in a very smoke-filled sky, you can see a very red sun, and you can see that it even looks a darker red down at the bottom because it's moving through, or the light is passing through even more of the atmosphere, at the bottom of the sun than it is at the top. And you might think it's not a much more, but there was apparently a gradient or a sort of a slope in the amount of dust that was quite extreme that day in the Earth's atmosphere. So the bottom of the sun looks a lot redder than the top. Now, going back, I hope I have, well, I meant to have another one of these, but when the sun is setting, okay, the blues and greens are all scattered out and absorbed. The things that make it through are the oranges, yellows, and reds. And if there are clouds lurking around up here, those are the colors that will be preferentially reflected by the clouds, because the blues and the greens near sunset are mostly absorbed. This scattering is less of an effect, but the absorption really gets rid of most of the blues and the greens, and even those that are scattered out of the atmosphere or whatever. So the upshot is it's the yellows and oranges and reds that remain, especially by the time you get down to here, and that's where the clouds are. Most clouds are not very high above us. This person does not actually take up 1/2 of the Earth's atmosphere. That would mean the person is 50 kilometers high, because in round numbers our atmosphere is something like 100 kilometers. So a person is way down here, and clouds are like right up there where his knee is. So by the time the light gets down to the clouds, it's mostly orange and red. So what remains is what reflects off of the clouds. And that's why the clouds are different shades of yellow, orange, and red at sunset. It's because those are the only colors that remain by the time the light has reached those clouds. And depending on exact atmospheric conditions, you get different colors. I love sunsets. I take lots of photographs of sunsets. And you get different shades all over the place. And this is a good one, in fact. Here it's actually raining over here. But you don't have to look toward the sun. This is sort of in the direction away from the sun. There's Half Dome in Yosemite, for those who know Yosemite. And I'm at Glacier Point, and I'm west of Half Dome, so the sun is setting on the other side of Half Dome, and here's all these clouds. But I can also look in other directions. Oops, I forgot to highlight that slide. But anyway, all around the sky, you can see clouds of different colors, and the colors they have just depend on what light is reaching them from the sun. So that's the basic point. And now you can go home and tell your parents and friends why sky is blue away from the sun and sunsets are some shade of red. Okay? And in fact, as we will see on Friday when we study the lunar eclipses in more detail, it's for this same reason that total lunar eclipses look some shade of orange or red. And many of you, I know, saw the total lunar eclipse on the first day of classes and remarked how kind of orange or red it looked. And it's the same sort of a thing. From the perspective of the moon, the Earth is blocking the sun, but a little bit of sunlight is making its way through the atmosphere. The blues and violets and greens get absorbed and scattered, so the only thing that makes it all the way through and reaches the moon are the oranges and the reds. So the moon, the totally eclipsed moon, looks orange or red for basically the same reason that sunsets look orange or red. So that's kind of fun, okay? You now understand that. And it turns out this is relevant not just for understanding the daytime sky, but later on in this course we will study nebulae, clouds of gas and dust from which stars form. And one way in which we find nebulae is by looking at the light that they reflect, and they tend to reflect blue light more than red light. Okay, let's now discuss the phases of the moon, unless is there a question there? Yeah, okay, sure. So what's your name? Pardon? Michaela asks, why do clouds look white when the sun is high up in the sky? That's a very good question. It's because sunlight is white light, and the size of the particles, the typical particles in a cloud, is big enough that they reflect all wavelengths of visible light roughly equally. No preference for blue over red. So since sunlight is white light, and the droplets in clouds are big enough that they don't care what the wavelength is. See, little dust particles do care what the wavelength is because they're close to the same wavelength as visible light. So then complex physical effects come into play. But droplets of water and, vapor clumping up and all that kind of stuff in clouds or ice crystals, which is what a lot of clouds are, they're big compared to the wavelength of visible light. So they scatter all wavelengths of visible light equally. So if what hits them is white light, what gets reflected is white light as well. Now, if what hits them is orange light, then, of course, there's not much blue to reflect, and they will simply reflect the orange light. That's a great question. Okay, let's move on to phases of the moon in terms of sort of fun things to understand. Here are the phases of the moon defined for you. New, crescent, first quarter, gibbous, full, gibbous, third quarter, crescent, new. Here I show them. Crescent, first quarter, waxing or getting bigger, gibbous. Full moon, waning or getting smaller, gibbous. Third quarter, waning, crescent, and new moon. That's a great picture of the new moon, isn't it? Yeah. Just go to PowerPoint, hit black background, and you get a picture of the new moon. All right, so there they are. Now, a lot of people think that the phases of the moon are caused by the shadow of the Earth, like during an eclipse, which is wrong, or by clouds on the moon and stuff, and that's wrong too. Turns out that the phases of the moon are caused only by the changing relative geometry, and that is the placement of the sun, moon, and the earth. Now, many of you have seen this before, so I won't belabor the point, but the sun is coming in from the right in this diagram, the sunlight, and it's illuminating half of the earth, and here's the night side of the earth, and the earth, of course, rotates through like this. We've got sort of a top view from the North Pole, and it looks like it's rotating counterclockwise. And the moon is revolving around the earth. It takes about a month, one moon, same origin for the word. So anyway, when the moon is between, or roughly between, us and the sun, the sunlit hemisphere that is, the hemisphere that reflects sunlight, is not the hemisphere that we see. That's the dark hemisphere, and it should look blacker here, but I guess the publisher didn't want to make it look exactly black because then it would be hard to see, but anyway. So you don't see the sunlit part, so that's the new moon. When a few days later the moon moves over to here in its orbit around the Earth, yes, the Earth has moved around the sun, so that relative orientation has changed a little bit, but it doesn't matter. The sunlight is, you can still draw the sunlight as coming in from the right. So think of the Earth not even orbiting the sun on this time scale. The sun is always coming in from the right on this diagram. It's only the position of the moon relative to the sun and the Earth that's changing. So here, a few days later, the sunlit half is still the half that points toward the sun. But the half you see, the hemisphere you see, is everything to the lower left of this little, segment that I'm drawing with my arrow here. And you see that there's a little pizza-like sliver that you can see. And because it's a slice of a sphere, it looks like a crescent. Now, a week after new moon, the moon is up here somewhere, the illuminated hemisphere is still the hemisphere that faces the sun. The hemisphere you see is the hemisphere that's facing us. So you see one half of the hemisphere that's facing us. That is, a quarter of the moon. The moon only reflects light. It doesn't generate visible light of its own, at least not in any significant amount. So the part you see is one half of all that is in principle visible. So we call that first quarter. Now, why is it called first quarter when you can see half of the facing side of the moon lit up? Why isn't it called half moon? Some people do call it half moon, but most astronomers call it first quarter. It's because it's a quarter of the way around the Earth in its orbit. Okay, fair enough. Well, then why don't we call the full moon the half moon? Because it's halfway around the orbit around the Earth. I don't know. There is no reason. It's an inconsistency. If you call this the quarter moon, you should call this the half moon, because it's halfway around. Or if you call this the full moon, you should call this the half moon. I'm sorry. I'm just the messenger. I did not think up the terminology. Anyway, going to waxing gibbous, now the hemisphere you see is nearly the same as the hemisphere that's lit up. So it looks like that. And then at full moon, the hemisphere you see is the hemisphere that's lit up, unless you have an eclipse, and we'll talk about that on Friday. So then it's full, and then you have the phases going the opposite way. And so here's a nice little applet where I can unpause the motion of the moon around the Earth. And you can see there's full moon, there's waning gibbous, there's third quarter, waning or getting smaller crescent, new moon, waxing crescent, first quarter, waxing gibbous, full moon, and so on. Now, just because I need to show you my t-shirt, it's inconsistent terminology. Can you see the moon during the day? Yeah, you can. A lot of people think you can't. It's just not as obvious during the day, but you can see it during the day. And I'll explain that in a minute. But since I'm wearing this t-shirt, let me explain Earthshine. Why is it then that during crescent moon you actually can see a little bit of the dark side of the moon, as on my, as in this photograph or on my t-shirt? See that? Went a bit slower today, but I told you about my trip. But why can we see part of the moon during waning or waxing crescent? Yes? Yeah, so the Earth reflects light onto the moon. If we're seeing a crescent moon, then what is a person on the moon facing us seeing for the Earth? A gibbous, a mostly lit up Earth. So the moon dude sees a very bright Earth shining light on it. That light reflects off of both of the directly lit up parts of the moon and the parts that are dark, that is in the shadow of the sun. And so that's what you see then reflected back to the Earth. Okay, I'll see you on Friday. Thank you.